progress. From an idea nurtured by our past and present ability to measure, the cornerstone of technological achievement. Today, our country is on the verge of a new industrial revolution, brought on in part by the introduction of the computer. At the National Bureau of Standards, that revolution is being supported by the Automated Manufacturing Research Facility, the AMRF, a research test bed studying fundamental questions affecting the modernization and competitiveness of American industry. John Simpson, Director of the Center for Manufacturing Engineering.
In recent years, the advent of the computer has revolutionized manufacturing. We are not alone in the belief that the factory of the future will look much like the computer installation of today, except that the peripherals, which are now printers and plotters, will have real muscles. They'll be lathes, milling machines, and robots.
But robots and NC machine tools take major capital investment, which many firms, small or large, cannot afford. Since 90% of the companies in this industry are small, the problem is major. The only feasible way for such companies to automate is incrementally. And to do this, they need the flexibility to buy from a variety of companies with the assurance that the equipment will be compatible. Interface standards are necessary to provide this flexibility.
It is necessary to have a control architecture which supports interface standards that are both technically sound and commercially acceptable. We believe we have developed just such an architecture and have demonstrated in the AMRF that such an architecture is both feasible, economic, and efficient.
The AMRF design is based on a hierarchy of control units, connected by a factory floor network and served by a distributed data system. By June 1985, this factory control architecture was implemented and tested to the cell level for 3 workstations. In operation, a large, complex task is decomposed at the highest level into a series of smaller tasks. Commands flow downward in the hierarchy, and status information flows upward. Each of these tasks is analyzed by a control unit at the next lower level, which repeats the process, down to the equipment on the shop floor. The data system is accessible from all levels. Process information, such as NC programs or vision data, is placed in the database by design and engineering systems. The data is called for as needed by the control hierarchy. This data-driven approach provides the flexibility needed to make any part for which data is present, without changes in the control system itself. Receiving commands from cell control, the materials handling workstation delivers needed tools and part blanks to the machining workstations. The horizontal machining workstation is the most mature in the AMRF. It is fully integrated with the control and database systems. Here's how it works. Upon receiving an order, the cell controller fetches a routing slip from the data system, schedules delivery of raw materials and tools, and coordinates production activities. The workstation controller then obtains its operation sheet from the database and issues commands to set up the workstation and make the parts. For example, it commands the NBS robot controller to load a part blank into a fixture. From the database, the robot controller obtains information about grip points, forces, and position, and controls the robot arm and grippers accordingly. The workstation controller then commands the NBS machine tool controller to mill the part. After obtaining the necessary machining data, such as NC programs or feature-based descriptions, the NBS machine tool controller guides the machining center through the milling, tool changing, and related steps of manufacture. The robot's real-time control system, pioneered at NBS, is particularly versatile because it reacts to a variety of sensory inputs, such as force, torque, and vision. This vision system is based on the concept of structured light. Bars of light are projected across its field of view while the vision computer observes how the image bends. It then deduces position and shape of the target object. From a description in the database, the vision system recognizes this IGES part blank and advises the robot controller accordingly. Fixturing workpieces for machining presents special challenges to the industry. NBS engineer Alex Slocum solved one of the challenges.
What we do then is we automate the process that the machinist does. We have two leveling bars whose height we can servo control. We have discrete stops which justify the position of the part in the jaws. And we can control the force that the jaws grab the thing with. So if you have a small, delicate, casted part, you won't smash it. And the biggest challenge of all is make it so a big robot can put a part in, can change the jaws so you can hold an odd-shaped part without requiring any special skill that normally a machine operator uses his vision, his mind, his ability to tap a part into place.
Needing a different end effector for handling this heavy valve body, the robot positions itself for a quick change at this NBS-developed device. Sensors in the holder are used by the robot controller to coordinate its activities. The modular structure of the control system makes it possible to expand applications as technology advances. For parts needing second surface machining, or in this case for proper position in the fixture, an active pedestal is utilized. A second gripper mounted on a rotary table under the control of the robot controller. In this laboratory environment, real Navy valve bodies, often difficult to procure, can be machined quickly and with consistent quality. This mechanism provides the flexibility to change tools if one becomes dull or broken, or if a new tool is needed to make a different batch of parts. When the robot cart detects its battery is low, it automatically stations itself for a charge. The successful small batch manufacturer will ultimately rely upon systems running unattended. At this turning workstation, sensors and process control systems are being studied. The gripper mechanism used on this robot is an experimental device developed at NBS. It is about half the weight and can exert 10 times the force of the best currently available. Interchangeable fingers have been designed to increase its flexibility. Several collets are used, giving the lathe the ability to handle raw materials of various diameters. collet controller contains sufficient sensory interactive ability to know whether the collet is fully engaged and how much force to apply as this mechanism pulls it home. Although collets are the most accurate of holding devices, they are also the most difficult to use because of tight clearances. Human interaction has always been a necessity in loading part blanks. Here is the only known installation in the world where a robot takes over this precision task. It does this with the help of the micromanipulator. Software designer Lou Greenspan describes how it works.
Now the micromanipulator takes the part and puts it in a collet. There is only 5/1000 inch clearance between the part and the collet. And it goes through a search routine until it finds the hole. When it finds the hole, it then relaxes and signals the controller and says, "I'm in the hole, you take over."
Longer workpieces require machining in stages. A programmable stop has been designed which pushes the piece into position. It is accurate within 100 microinches. Through laser interferometry,